I promise you I won't keep you a minute longer than I need to. It also depends on you asking me simple questions at the end. Just kidding. All right, so let's get started. Okay, a little bit about myself. My name is Pramod Immaneni, or people also call me Pi. Principal architect in the data platform team at Rivian. I grew up in India in a city called Hyderabad. Now I work in Bay Area, San Francisco, in Rivian. This is my first time visiting Belgrade, Serbia, and it's been a great experience so far. All right, so a little bit about our vehicles. You may have seen our car outside in the front. So we make electric vehicles, no surprise. So we actually make 3 different vehicles. The 2 you see in the picture here are our truck and SUV. They are built to do both on-road and as well as off-road. They are very adventurous vehicles. You can take them if you want to climb, go actually scale rocks with this. You can still do that. And earlier in the talk, my colleagues actually showed a video of the different drive modes that the vehicles support. We also have a electric delivery van, which Amazon uses in the US to deliver parcels. And now it's actually open for anyone to buy, actually. The truck, R1T, was our first model that we started selling, and SUV is the second one that we introduced. And the very first year that our vehicle was introduced, it won the Truck of the Year award, and so far it's sort of won many accolades from sort of a lot of respectable institutions. Okay, so the main features of our vehicles are basically it's built up from ground up to be a software-driven vehicle. Every aspect of the vehicle is software controlled, not just what you as a user may see, but in fact the vehicle dynamics, the suspension, all of these are actually controlled by software algorithms and can be updated, right? So in fact, we recently pushed a software update that actually improved the comfort of driving on sort of dirt roads, for example. So to do this, it's no secret we need data, right? So we have sort of various controllers in the vehicle and sensors that are sort of constantly monitoring, measuring, and collecting data, right? A typical vehicle could be actually measuring 1 million data points every second, right? But we don't need all of that data, not so much data. But we have sort of the signals that we're looking for that are sent to the cloud by the vehicle. And we have both sort of real-time collection that happens, and there's also sort of a batch upload / on-demand pull of the data that happens, right? So these are what we call low frequency and high frequency streams. You can see at the bottom of the screen. We have streams that come in real time, which don't have to be don't have to be highly sampled, and then we have high sample data that we can pull on demand. Apart from that, we have other data. For example, if you're using our chargers, we have a number of chargers installed at different locations, so we have that data, as well as if you bring your car for service, we have service data. So all this data comes into our platform, and then we power the various applications in our company, right? So we have applications that internally our teams build, for example, for diagnostics, for doing reliability, or on the service side when you take your vehicle to service, or even you as a user in your mobile application, right? When you want to see the status of your vehicle, or you want to send some quick commands to the vehicle, like turn on the AC before you enter the car. So we have a platform that does both real-time and near real-time processing, as well as a data lake that basically our different machine learning AI engineers can use to build models. And so sort of these 2 sub-platforms that are in there. And of course, on the top, you have sort of the output, which is kind of the applications and the models that the various teams are building. Right. So the two, so a little bit into the two architectures that inside our platform. So we have a real-time part, which is here the focus is on being able to act on the data immediately as soon as it's available. This could be, for example, some critical alarms or data that needs to be presented without a lot of delay. For example, you as a user, when you open your mobile phone, you probably want to immediately see the state of your vehicle, right? It can't wait. But then for some of the other sort of analysis, like reliability, or for example, even when you when you have a problem, or you make a service request, those things there's probably a few days lead time, so they can use our data lake to be able to kind of get your data. So on the real-time side, we have a number of data pipelines. These are built on top of Flink, which is a streaming platform, which I'll go a little bit into. And we also have a low latency OLAP store where all this sort of telemetry is available, and sort of various teams can sort of query this internally. And on the data lake side, we use Spark. In fact, the prior talk, if you remember, the speaker talked about a lakehouse architecture, right? We use that. So here is basically where the data is available for longer periods, and you can actually, if you require, there are teams when they're trying to build models, and they're looking for a lot of data, for example, for like a month of data or long periods of data, they can use the data lake to fetch that. Okay, so in this talk, I'll focus more on the real-time side. So the goals here are, what we're trying to do is basically make sure that the data that we make available to the various teams in the company is fresh. When these teams are asking for the data, we're able to return the data quickly, so it's low latency. And the other facet of this is that sometimes you need to take actions as the data is arriving. So it is not query anymore. So there are teams that are looking for certain patterns of data, and when the data is available, they want to be able to take quick actions, right? So these are the three tenets for the real-time side. So what are the different services that we provide here, right? So in this picture, I'm sort of broadly covering the three parts. So the top one that you see is our query service. So the vehicles, they are sending this telemetry data, which is basically a time series data containing the signals, the various sensors signals, and they're basically the signal values. After doing some standardization, some cleanup, validation, some anonymization for governance purposes, and so on, this data is stored in our OLAP store. We use Druid there. And then we have a query service that adds other vehicle context and then makes it available for downstream applications to be able to query, right? So here they can slice and dice. They can make time series queries. So for example, if you're on your mobile phone and you want to look at your charging stats, right? How much did you charge the vehicle this whole week, and bucketed by day, and you want to see a chart of it, right? So they would be making those queries to our real-time service, and you want to see that quickly, right? The second kind of services are things where an action needs to be taken, right? For example, when there's a critical alarm, right? We want to be notified immediately. For example, if there is some sort of a collision event or something like that, right? And then the other examples there. So for example, when there's an OTA update, we want to send a quick notification to your mobile phone that the over-the-air update has been completed, right? And then there's some engineering fleet examples. So internally engineering, when we upgrade the hardware, there are several parties that want to be notified so they can do some bookkeeping. So those things are also powered, right? So these services is what we call Event Watch, and then our teams, users can actually also submit this is a configurable service. They can submit the patterns of events they're looking for, and we can quickly deploy those pipelines for them. And the last at the bottom you see are actually custom pipelines we built. So these are more the pipelines which a little bit more complicated logic. They're still real-time pipelines. One, for example, is geofence. So, for example, we suppose we want to know when a vehicle enters a particular geofence or when it's leaving a geofence. We want to be notified, right? So these are mostly also for engineering and fleet vehicles, basically. There's also some session detection which happens if, for example, you want to do like a drive session or a charging session. So those kinds of pipelines are sort of custom pipelines. All right. So let's look at the for the stream processing what the deployment stack looks like. There's nothing special here. It's sort of fairly vanilla. So we of course we run on cloud. We use AWS. And all our stream processing runs on top of Kubernetes. We have EKS as a clustering layer, and then Flink is our sort of stream processing layer. And I'll explain in a bit why do we need the stream processing engine. And on top of it is where all the pipelines are written, right? So if somebody is building a custom pipeline, it would be basically built on top directly on top of Flink. If you're using our Event Watch service, which is the configuration-driven service I talked about earlier, where there are available configurations and you can just specify the signals you're looking for, then you're mainly kind of creating configurations, right? Okay. So a small sort of primer on stream processing. So many of you may already be familiar, but for those who aren't, I just wanted to sort of give you a quick catch-up here. So the difference between stream processing and batch processing is essentially here you want to be able to process on a true event by event level, right? Especially basically as soon as an event is produced or available, you want to be able to apply some logic, right? So the reason we use Apache Flink is it's a sort of a true event streaming platform, as opposed to maybe something like Spark, which is more of a micro batch platform. So why is that, right? So basically, when you're trying to batch things, there's an inherent latency, right? Because the entire batch has to be formed before it can be processed. So with stream, you basically don't have those latencies. So that's the main reason, right? So the other important part of stream processing is scale, right? You want to be able to do this processing, but also be able to handle the scale at which the events are coming in, especially from our vehicles, right? So today we're dealing with more than sort of 2 million events per second, and it's growing kind of continuously. Right? So not only at scale, but we also have to make sure that when the stream processing, when it's running, it's going to be running continuously, right? It's not going to be shut down. So which means we have to be tolerant to failures. So if nodes go down, containers go down, we need to be able to make sure everything gets recovered in a stateful manner. Right. Okay, so just the anatomy of a pipeline, of a data pipeline, a stream processing pipeline. Essentially, whatever logic that needs to be that needs to be in your pipeline, you actually break it into logical sections. These are called operators. So in this picture, you see there are 5 operators. Those are the 5 dark blue circles. And you kind of break your logic into these parts, and then you connect them up. And these APIs for connecting this up is what the stream processing engine would kind of provide you. And then basically each of these pieces of logic are kind of doing one logical operation, and they are kind of working on stream of data, right? So essentially they'll be given each piece of data as it arrives. They can do some work and just return a result, and that gets forwarded by the streaming engine to the next operator down the pipe, right? So this is a graph. This is called a direct acyclic graph or a DAG. And these this DAG together is your application or your single pipeline, right? Now you can choose to run these different operators in one thread. That's like there's no real benefit if you do that, but because essentially you're putting it all on a single processor, right? Or you can choose to separate them into separate threads, or you can choose to decide to run them on different machines altogether, right? So that's where the scale comes in, right? So to handle higher throughputs, this sort of, when you're kind of separating out, you're getting the pipelining benefit, right? So in operator 2, let's see. So when this operator is kind of processing a piece of data, an older piece of data, this one's free to process the next piece of data, right? So this is sort of standard pipelining. Now, not only that, now each of these pieces of logic can be further parallelized to run in multiple threads or multiple processes, right? So your given data can be sharded and partitioned to kind of spread across multiple processes, right? So that kind of lets you horizontally scale, right? And all these things are kind of running on the Kubernetes cluster. And some terminology, so each piece of data, we call it a tuple. This collection, this kind of stream of tuples is called a stream, and these are operators. Okay. All right, so that was sort of theory, right? So let's look at a practical example of one of our custom pipelines. So this is a geofence detection pipeline. So imagine, we have users that are creating a bunch of geofences. These are polygons, and we want to know if a particular vehicle, a fleet vehicle, enters one of these geofence, right? So the brute force way is, I can look at the location and then I can check against each geofence, right? But that's going to take too long of a time. It's not going to work, right? You won't be able to keep up with the million events per second or whatever that's coming in, right? So you need to play some tricks. You got to do something smart, right? So this one uses, for example, a geohash strategy. So geohash is a way of kind of breaking down your location, a way of categorizing location. So if you look at this little map below here, so basically the entire world map is divided into 32 regions. These are these 32 boxes, right? And each of them is given an alphanumeric character. And then, so that's this first character here. So for Sava Center, right, the first geohash code is S, right? Now each box, this is pretty big boxes, right? They're like, I think 6,000 kilometers by 6,000 kilometers or something like that. So each box again is divided into 32 subparts, right? And for example, and if you keep going down that way, right, the Sava Center ends up being SRY, this 12-letter alphanumeric code, right? That's our location here, right? So what happens is, what we do is we actually have these, so we have this vehicle stream that's being read in from Kafka, and then we have these 8 operators, right? Each of them is almost sorting, right? So for example, this level 1 operator is just looking for, let's say this is one geofence you created on Sava Center. Then it's basically if a vehicle has, it takes the location of the vehicle, converts it into a geohash. If the geohash starts with S, it puts it into the Sava Center bucket, right? So here it's kind of basically just looking at the level 1 is just looking at the first geohash character, right? Level 2 is looking at the first and second, right? So by sort of kind of breaking this up, we are kind of bucketizing it, and we are kind of organizing the vehicle into the kind of the right bucket, right? By the time you reach level 8, we have basically the geohash of the vehicle's location into a bucket, and all the geofences that the users have already created for the bucket. So the last bit is we're just going to only have to check the the geofences that are in that particular bucket, right? So it greatly simplifies the problem. As opposed to checking across all the geofences, we only have to check the geofences in that one bucket, right? So the other advantage is now these can all be pipelined. So essentially each of this is a separate operator. So we are able to kind of process new incoming location samples while the previous samples are still going through the pipeline. Okay. Okay, so that is a custom pipeline. There are some use cases that fall into custom pipelines, but most of the times, our users are not trying to do custom. They're looking for simple things like they want to know when a particular signal on the vehicle is activated, or they want to know when a particular, let's say, value of particular sensor goes above a threshold, right? So we don't want them to have to build applications in those cases. So for that, we have a sort of a ready-made service we call Event Watch. It's basically the same thing. It's actually a pipeline internally, and it's kind of exposing a configuration-based approach for our users, right? So there are, and the next sections are kind of go through what kind of configurations it supports. But the basic idea is it's allowing you to do kind of basic pattern matching of events, and then it's able to kind of filter those events out and give you those events, right? And then we support a number of backends. So essentially, you can send those events out to PagerDuty or to mobile notifications and so on, right? So this particular platform, again, it's kind of processing about 2 million events per second and kind of with less than 100 milliseconds average latency, right? So you can basically detect an event within 100 milliseconds of it happening, right? So some of the basic kind of configuration it supports. So the first thing it supports is streaming SQL. So you can express what you're looking for as a SQL query. So this is a continuous SQL query. So you can say, oh, I want a particular signal from a vehicle. Right? So as soon as that signal comes in from the vehicle, a substream is created and sent to the receiver, to the user, right? And this is a stream that you're going to get continuously on a Kafka topic. So it pops up. So yeah, so so you just have to receive it and good to go, right? But as we kind of were building the system, we kind of came across sort of a number of cases which we need to handle. For example, our users did not care, said, okay, we don't want events that are older, right? So you may have, for example, an alarm that gets created now, but maybe the vehicle's out of range and it comes back out of signal range. It comes back into connectivity after 2 hours, and then the event goes to the server, to the cloud, and at that time it may not be of use to them, right? So they can define a staleness, so which is basically what's the difference between the event time and by the time it was received, right? And if the event is older than a particular staleness period, they don't care about it. So those are things that can easily kind of specify through configuration, right? So another one is dedupe. Sometimes a particular there may be some signals where a particular state in the vehicle gets set, and it sort of keeps on repeating and kind of sending you that the signal has been signal value, but you may not care. You may just want the first trigger, right, when the state was set, and you don't want subsequent re-reporting of the same value. So you can kind of specify that to kind of dedupe those events. And last is kind of interesting. So you can actually have state. So for example, in this example, you basically want to know when pet mode is on, if the charge becomes critically low, you want to know about it, right? Or you want to get a mobile notification. So pet mode is essentially you can leave your pet in your car and then you can do some things and come back. So it'll keep the HVAC, it'll keep your AC system on your vehicle. But if your charge is low, then it's a problem, right? But these are two separate events in time. So you may start pet mode at T1, and then the charge may go down at T2, right? So the system has to remember, right, that a pet mode has been on or before, and later on the charge has gone below a threshold. So it can do that as well, right? Okay. All right. So that was our event streaming service. So next, I'll spend a little bit of time on our query service, which is kind of more common, I guess, right? When you're kind of dealing with data, you're querying data. So here, like I mentioned, so we basically are storing this telemetry data that's coming in a distributed OLAP store. We use Apache Druid here. And then we kind of expose that through a query service. And where is this used, right? It's used by various teams in the company. For example, if you have a service request, then the service team can pre-download your data related to the problem. So when you go there, they can quickly work on fixing the problem as opposed to figuring out what's going on. Or for example, if there are parts needed, they can order parts, right? For fleets, the fleet managers can look at the state of charge. They can look at locations. They can do charging stats. So a number of things, right? As a user too, you can for example look at your charging profile and so on, right? Okay. So we'll look at next at how and this particular service, so this is all the telemetry data, right, over multiple months, and we are able to kind of serve this at kind of sub-second speeds, right? So essentially, if the query comes in for the latest data or for data that's a few months old, we need to kind of answer these queries quickly. Okay, so the core enabler of this is Druid, and which is the sort of a distributed OLAP engine underneath, and then we also actually contribute to Druid. So it's for those who are not familiar with it, it's a distributed database. It kind of has a nice balance between real-time features, performance, and sort of scale, right? So the one of the core requirements here is that the data has to be time series data, which is in our case it's time series, so it's kind of good. What it excels at is being able to query both real-time and historical data at sub-second latencies, and it's an easy scale by adding more nodes, and you can you have a lot of control here. You can actually scale various parts of the system. You can scale your query separately. You can scale your data nodes separately. You can scale your real-time nodes separately, and it kind of gives us a lot of that helps us kind of keep costs, control on costs to be very tight. And oops, sorry. Okay, and sort of get the best performance that we can, right? And just natively, it supports OLAP queries, so you can slice and dice on sort of these various signals. So you can and you can sort of time bucket them. So you can ask, for example, okay, in the last week, give me total charge for these 5 vehicles, right? Or for example, if you're a fleet, give me a total charge per vehicle over the last 5 days, right? And it'll get you pretty quickly, right? Or total charge with some location as a combination, right? So all kind of permutations and combinations of your features, it can sort of do those things pretty quickly. Okay? And it's quite extensible. It's open source. It supports a number of plugins. For example, our real-time data is in Kafka, so it needs to be able to ingest from Kafka. We use S3 as a sort of long-term storage, so it has kind of inbuilt plugins for all these systems. Okay. So yeah, wanted to kind of go a little bit into the real-time side of things here. That's what the talk is about. So so the way a real-time ingestion into Druid works is, so we have Flink pipelines that are writing to Kafka. So as you know, Kafka is a distributed message queue. So a single topic is actually spread across multiple nodes as partitions. So the data is kind of being written parallelly to multiple partitions. And then in Druid, we actually run a number of ingestion tasks, and these tasks are parallelly consuming from these various Kafka partitions, right? So we can, for example, have different mapping ratios here. For example, here we can have single task reading from multiple Kafka partitions if the throughput is low, or it can go one-to-one, right? We can also have multiple tasks reading from the same partition, and you may ask, what's really the reason for that? The reason for that is essentially for fault tolerance, right? If one of the nodes goes down, if this task goes down, if there's a copy, that means that the ingestion is still going on, and there is things don't have to go back to the previous checkpoint. Otherwise, things have to kind of go back a little and restart, right? So that gives us that a lot of flexibility there. So these tasks, they are ingesting this data, so at sort of given throughput, and then and they create these things called they create these index files called segments. And once the segments reach a certain size, they get pushed to S3, which is the deep storage, so that they're now lost. And then they're also pulled in by what are called historical nodes. which basically answer to queries that the users from the apps, right? So when a user is, for example, querying data, depending on the time range, if the time range is totally on historical on the historical side, basically it doesn't overlap with the latest time range, then the queries are being answered by the historicals. Whereas if the queries are on latest data, then they're being answered by these ingestion tasks directly, right? Or if the time range includes both historical and real time, then the result of both of these things are being queried, and the results are being merged here by the brokers and returned, right? So it's a nice scalable architecture, nice componentized architecture, and we can scale the brokers independently. We can scale these ingestion tasks independently, the historicals independently, depending on needs, right? So for example, if you want longer and longer retention, we'll basically have larger and more historical nodes, right? If we have higher and more higher throughput, ingestion throughput, we'll scale the ingestion tasks. If the number of queries increase, number of users querying increase, then we'll increase the query brokers, right? Okay. And then, of course, everything is checkpointed. Everything is stored in deep storage. So nothing is lost, right? In fact, if the entire cluster goes down, right, no problem, right? When we start up, the last checkpoints are loaded from the deep storage, and then the ingestion tasks continue, right? Because here we use Kafka, the data is all preserved, right? They're going to go back to the last checkpointed offset, and they're going to continue. Okay. All right. Last but not the least, this is our Kubernetes deployment. We basically run Druid on Kubernetes as well. We have separate node groups that we're using. For example, the master nodes, which are sort of coordinate all the activities. So we can kind of allocate the resources for these appropriately. The data nodes, of course, require a higher number of resources, so we put them in a different node group. And of course, query nodes they need sort of in between. They don't need as much resources as data nodes, so we can put them in their own node group. And then essentially each of them kind of run as replica sets. If anything goes down, they get restarted by Kubernetes. And then there's a protocol that kind of gets brokered through Zookeeper, where for example, if a data node goes down, the coordinator immediately assigns that work to another data node. And when it comes back up, when Kubernetes restarts it, it gets advertised through Zookeeper, and then coordinator knows it's available and starts redistributing the data load, right? Yeah, I think past time. Yeah, so that's it. Thank you for staying. And then Rivian is hiring, so our team is growing here in Serbia. So if you're interested, please do apply.
Thank you very much. Do you have some questions? Yes? Microphone, please. No, here.
Thanks for the presentation. How do you backfill data? Do you in the case that data is no longer present in Kafka? So in case you have some bug or anything else that bad data goes into the system?
Yeah, so we have we have retention in Kafka, but as you can see, the data gets pulled into Druid pretty quickly, and then Druid has a multiple month retention, and it's getting stored into S3 anyway. So it's
yeah. But in case that you push some data into Druid that is not correct, for example, there was some bug on the backend system that pushed that change, and you are no longer able to.
A good question. Oh, I got the question. Oh, yeah. So if you remember my original picture, we also have the data going to Delta Lake, right? So we'll pull in from the Delta Lake and reprocess. Yeah.
Thanks.
Anyone else? Yes.
Thank you for the presentation. Are you working only on the raw data, or you do some aggregation too for Druid specifically?
So here, for Druid perspective, it's raw data. We are able to actually provide the raw data without having to resort to aggregates. But we do create purpose aggregates for sort of different applications that need them, mostly on the Delta Lake side. But here we are able to kind of handle.
Thanks.
No, we don't have to do those. We are able to we have actually made some performance improvements to Druid as well to kind of keep up with the load. so far.
Thank
Thank
you.
you.
More questions? No. Pramod, thank you very
Oh,
much.
thank
We
you.
are enjoyed in your work.
Oh, thank you.
Thank you.